to have Alexios Polychronakos from the City College of New York, who is going to talk about dual formulation, solitons, and fluid mechanics in generalized Calogero models.
Okay, it's great to be here. Thank you for being in this room on a July day, where most people are off to better endeavors. Anyway, today I would like to tell you a little bit about some recent work in progress that I've made in the Calogero model, which has been an object of my fascination for a while, and fascination, I guess, to some of you, like Vincent, I guess, and Dina, sorry. It's impossible not to offend someone when you try to give references to people having worked on the Calogero model, because by the zeroth approximation is that everybody has worked on it. But be that as it may, I will start with a short introduction and review, encouraged by Vincent, I guess, that the Calogero model is simply a model of particles on the line, usually non-relativistic, although there is a kind of relativistic generalization, that have this standard kinetic term, but they interact with two-body terms that are typically of the inverse square type. That is, the potential is inverse square, therefore the force is inverse cube. It's not like the Coulomb potential. That's the short distance behavior of the potential. There are generalizations where at longer distances this is different, but this is the generic type. And this was first introduced by Calogero, Francesco Calogero, in 1969. He is a nuclear physicist, theoretical nuclear physicist, and he was looking for solvable few-body problems. So actually, before I go that, actually he first solved the three-particle problem quantum mechanically, because quantum mechanically was the interesting problem to solve. And having solved the three-particle problem, he soon realized that in a very similar way, the n-body problem can be solved. Now, what would be the problem? The problem is that when you have many particles, other than the obvious integrals of motion, conserved quantities, which would be the total momentum in the absence of external potential, so no term there, and of course the overall energy, usually there are no other conserved quantities. So if you have more than two particles, three or more, the problem is generically not solvable or integrable. This was, so that was quite a surprise.
I have a question. Is the n-body wave function for this model known?
In some way, yes. I'm not aware of an explicit expression of it for arbitrary n. You can work it out for small n. The wave functions for the problem where you have an external harmonic oscillator potential, so the particles are in a harmonic trap, can be worked out explicitly for any finite n. But there is no general formula other than formal expressions that I know for arbitrary n. And please, if anybody knows anything more about that, let me know, because that's an interesting question, actually. Now, as I said, the original problem consisted of these particles, and there was an external potential that was a harmonic oscillator potential, and that was the original system that was solved. Later on, this was generalized for the external potential, the one-body potential, to contain cubic and quartic terms. This was done first by Zemtsev, but he had a restricted form of that potential. Unknown to me, his work, I also did it for a general set of potentials. I will talk a little bit about it, but that's where we stand today. There are generalizations that have to do with the two-body potential, Sutherland, Moser, etc. And the interest in this system from the physical and especially the mathematical point of view is that it is integrable. That means, I guess it was initiated by Moser and then many people contributed, that is, there are as many integrals of motion in involution, commuting with each other, as there are degrees of freedom, which is the definition of an integrable system. So here is a little cartoon of the motion of three particles that shows you why this system is interesting. This is a space-time diagram. This is space and this is time running upwards. So you start with no external potential, so the particles only have the inverse square interaction. And you start with a state where the particles are far away from each other, and they approach generically with some asymptotic momenta. That's this asymptotic region. So they move on these straight lines. As the particles come close to each other, assuming that the interaction is repulsive, because an attractive interaction, at least classically, is singular, the particles suck into each other and disappear. So as the particles come close, they repel each other, so they start steering away from their asymptotic paths. And generically, when that happens, you expect the particles to re-emerge from that interaction region with 3 new momenta and asymptotic positions. Surprisingly, for the Calogero model, not only do they emerge with the same asymptotic momenta as before, that means these slopes of these curves are the same, but they also emerge on the exact same asymptotes. There isn't even a parallel shift of these asymptotes as there could be, which means that not only are the asymptotic momenta conserved, but also the impact parameters are conserved. Another way of saying the same thing is that there is no time delay that the particles experience while they are interacting. If you don't look closely to that interaction region, if you just look at asymptotic data, the system is indistinguishable from a system of free particles. Quantum mechanically, that translates into the fact, when you do it, that of course the asymptotic momenta are conserved, but also the scattering phase shift must be momentum independent, because remember that the derivative of the scattering phase shift with respect to each momentum is the time delay that the particle experiences in the interaction region. Those are 0, therefore you just get a constant, and it's a suggestive constant. It's a constant that has to do with the coupling constant of the potential, and it contains 1, 2, 3 times that constant, 1 for each virtual two-body interaction. There is the fact that the system is so close is related to the integrability, and it's also related to the fact that you can view the system as a bigger system in which motion is free, which you have kind of projected down. You look at the shade, in quotes, of that system so that it looks non-trivial, and that's the matrix formulation and the Lax pair formulation. I will talk a little bit about it today, but I will mostly focus on other aspects. But this is just a flavor of why it is so special. You can put the particles in a periodic box of length L. So this is the box. So these are 2 particles here. That means that each particle can interact with each other particle, not only in the fundamental domain, but also through all the images of that other particle in all other infinite repetitions of that domain. So you end up summing that two-body interaction for all the images. And when you do the sum, you discover that this is 1 over sine square, which is exactly the same result that you would get if you thought that the particles are in a physical circle in 2 or more dimensions and they interact through the chord length. That's, to the best of my knowledge, just a coincidence. It's one of the coincidences of this system. There is no guarantee that if you take an interaction and you sum overall periodic repetitions, you would get the same interactions for the chord length, but it is true for the inverse square one. And this system, in the absence now of any external potential, the circle serves as a box to keep the particles together, is still integrable, and that's what we call the Sutherland model. Interestingly, it remains integrable if you add external potentials that are, of course, periodic on the circle of a general sinusoidal form, but restricted to the first 2 Fourier modes. That's the lowest Fourier mode, so a cosine that winds once, and that's the next highest Fourier mode. The system remains integrable. Why is the system interesting other than it being cute and having surprising properties? Well, it has this tendency of popping up in various situations of physical interest where you would probably not expect it or least expect it. One of the earliest and most famous one is its appearance in the interface dynamics in stratified fluids. Assume that you have a trough, a one-dimensional trough where you put 2 non-mixing fluids, so they form a flat surface. Motion is one-dimensional because you eliminate all excitations normal to the trough. And you're interested in the motion of the surface that bounds the two fluids. Imagine oil and water, so there can be waves if you slosh the system. This system was first examined by Benjamin and almost simultaneously by two more people, Davis and Akrivos. And eventually, 10 years later, almost, Ono expanded upon the mathematics of this problem. So it's usually referred to as the Benjamin-Ono model. I don't know why these other people were forgotten, but that's okay. And it turns out that the equation that this interface satisfies, which depends on one space and time, is a nonlinear, non-local interaction equation. This term here is the famous Hilbert transform that in the Fourier domain it just means that you take negative frequencies, you take the negative frequencies and you multiply by minus sign. So it's like a step function in Fourier, in the Fourier domain, but it's non-local in the real domain. And surprisingly again, this equation admits soliton solutions whose guiding centers behave exactly like Calogero particles. Solitons means that their shape does not change as they move. It also means that when they scatter, when they pass over each other, of course, when they are close, their shape distorts, but eventually they re-emerged with the exact shape that they had before when they move away from each other. And if you take their center and ask what's the equation of motion of that center, you see that it's exactly the same as the motion of Calogero particles. There are many, many other applications. I will very briefly try to mention a few. You can add spins to the particles. That was done by my collaborator Joe Minahan and myself, and Kawakami, Hikami, and Wadati, and eventually other people. You can consider spin chain models, and the standard physical application is macromolecules, where each molecule has a spin, and there is not only a nearest neighbor interaction, as is typical of the Heisenberg type chains, but there can be next to nearest and next to nearest, etc. And if that interaction can be approximated well with an inverse square decay of the ferromagnetic or anti-ferromagnetic interaction between the spins, this is called the Haldane-Shastry chain, and it is also solvable and integrable, and its excitations have the properties of Calogero particles. If you look at the spectrum of those excitations, etc., it's the same as that of Calogero particles. You can generalize that to a lattice that is not equidistant. That means that these distances here that determine the strength of the interaction are not constant. And for a particular such lattice, the model remains integrable, and that's a generalization that we have. Because of the fact that these particles behave almost like free particles, you can reinterpret the system in a certain sense as particles obeying fractional statistics, either through their scattering properties. If you look at the scattering of this system and you ask what is the dynamics of this system, you wouldn't be able to tell it from a free system, but of particles obeying fractional statistics, or from the way that the energy levels fill the phase space, and that's the exclusion statistics, usually attributed to Haldane, but a Russian physicist, Sergei Isakov, who has now left the field, had done it a little bit earlier, but as usual, credit goes to whoever popularizes it or better. Because of all these connections, the Calogero model can be used for effective descriptions of fractional quantum Hall states. It is relevant to two-dimensional gauge field theories. You can reduce them and you get Calogero particles with spin or Sutherland particles. And it has a horizon in all kinds of contexts: black holes, quantum field theory, matrix model of quantum gravity, string theory, quantum topes, mathematics of root systems, etc., etc. And there's no way that I can do justice to everybody. Apologies to people who have worked and have not thought of adding to this page. Quickly about the integrability in the presence of one-body quartic potentials. As I mentioned before, Calogero particles can be thought of as the reduction of a bigger, simpler system, simpler in the sense that the dynamics are simpler, in fact, in some sense free. And that bigger system is a Hermitian matrix in the most usual situation of the Calogero rather than the Sutherland model. The dynamics of that Hermitian matrix, denoted M, is the same as that of a particle in an external potential V. That external potential typically is a harmonic oscillator. So if that V is a harmonic oscillator, you would have only this term. This is a linear second-order equation that can be solved. Each matrix element of that matrix evolves as a free particle. If you now ask the question, what happens to the eigenvalues of that matrix? Under some conditions, these eigenvalues move exactly like Calogero particles. So the eigenvalues have a nonlinear evolution because the diagonalization from a matrix to the eigenvalues is a nonlinear transformation, but they arise from a simple system. That system, which is the Calogero model with the harmonic term, these are simply forces proportional to M itself, is the original Calogero model, but it remains integrable if you add quadratic and cubic forces, so cubic and quartic potentials. And the Lux matrix, the matrix that tells you that this system is integrable, is this one. This is a matrix that is not conserved in time, but its time derivative is the commutation of this with another matrix, which I didn't write. And if you have a relation like that, that means that the eigenvalues of that matrix are conserved, and these eigenvalues or their symmetric sums of powers, polynomials, will give you all the conserved quantities. The lowest one is the Hamiltonian. This does look like the energy of this model. These commutator terms upon taking the trace drop, but there are also higher quantities. One can prove that this matrix gives rise to conserved quantities in involution, but the proof of this which is means that the system is integrable, but the proof of this integrability is, well, a little bit complicated algebraically, but it simplifies dramatically in a case where this term, or rather the potential that gives rise to this term, is a perfect square, which I usually call a Bogomolny form for various reasons. That's actually the case that Inozentsev had studied. It is suggestive that this potential is special in that the integrability becomes a lot more obvious, but it doesn't have to be. The general system is still integrable. You can generalize that to unitary matrices, which gives rise to the periodic Sutherland model, etc. The last bit of review that I would like to do is the hydrodynamic, the many-body dense particle limit of these systems. If you consider many such particles close to each other so that when you go at a distance they look like a fluid, they look like a dense collection of matter, you can trade the dynamics of particles for the dynamics of the fluid, and that fluid will have a density, which we call rho, and a velocity, which we call v, functions of space, of the position on space and time. And using, again, techniques that derive directly from the quantum mechanical formulation of this problem, it's surprising that many of the things were first done quantum mechanically and then classically, using the established technology of what is called collective field theory. These three people, and thank you, Vincent, for correcting me. I had cited two other people. Actually, these were the first ones who did it. Andrich, Yevitsky, and Levine found that the Hamiltonian that describes this fluid is given by this. It has the standard kinetic term 1/2 rho v square, but it has it has this external potential term. It's rho, the density of particles, times the external potential, but it has this interaction term that arises from the Calogero interaction. It involves, again, this Hilbert transform. And this is the Hamiltonian in the sense that if you assume that rho and v satisfy the standard fluid mechanical Poisson brackets, this is like a U1 algebra, but this can be classical, then the equations of motion of rho and v are implied by the Poisson brackets of these quantities with that Hamiltonian. This system, of course, supports small amplitude waves. These are sound waves, but it also supports large amplitude waves that you can find exactly, and also solitons. That's again the hallmark of integrability, but in the language of the fluid system, it's not obvious why it is so. And the existence of these waves and solitons was generalized in a work of Abanov and Wigman, and later elaborated there, into the fact that you can find chiral solutions. That means solutions that move only to the left or to the right of arbitrary shape, and also solitons when you have either the free system or the system with the external harmonic oscillator potential. And that concludes the status quo, if you wish, of what is known about these models. If you have any questions or remarks at this point. Well, let's move on then to something that will bring us to what I would like to talk about today. Abanov, Gromov, and Wigman, when not in their first paper, but later on when they formulated this kind of chiral decomposition of this fluid equation, they ended up by rewriting the equation of motion of the Calogero model in this way, which we call now the dual, or they called it the dual formulation. Xj are the Calogero particles. J is the index, the particle index. We assume that they are all in an external harmonic oscillator potential of frequency omega, and G is the strength of the Calogero interaction, the inverse square interaction. So the particles X satisfy this equation that involves these extra variables Za, and the Za themselves satisfy a very similar equation. So it's like having two sets of particles, the particles and their duals, if you wish. If you take now these two equations together, and you take a second derivative and eliminate the first order terms by using these equations again, you find that the equation of motion of the x's closes among themselves. It does not involve the z's anymore, and similarly for the z's. Notice also that these equations are complex, but the second order equations are real. So this first order system gives rise to second order Calogero dynamics. The price that you pay is that you introduce these extra variables z. I stress that this is true no matter what the number of x's and z's are. They don't have to be equal to each other. You can take n particles and m different z's, and still the equations will close to the Calogero one. And so that calls for an interpretation of what these extra variables are or do, which is what I expound there. It turns out that these En represent soliton guiding centers. That means if you have a finite number even, but a large number so that we can visualize it better, of Calogero particles, and you slosh the system a little bit, they will start moving, and some of these motions look like soliton motions. The particles become denser at one point, and eventually a particle may shoot out, come back, etc. And these motions have a guiding center that is actually represented by this complex variable Zn. The real part of that variable is the guiding center, while the imaginary part of that variable is related to the width of the soliton. The closer it is to the real axis, the narrower the soliton is. When it goes away from the real axis, the soliton becomes diffuse. And interestingly, these solitons, when you take the large particle limit, reproduce the solitons of the collective fluid formulation. The fact that the number of z variables is less than the number of n variables means that you do not have the full motion of the system. You have a restricted set of solutions for that system. You recover the full phase space of the system when you have as many solitons as you have particles, in which case you have a complete duality. And the same system can be described either in terms of the particles themselves, that fixes the motion of the solitons, or the solitons, which can be viewed as the dual variables, and in some sense the particles can be described as condensation of solitons, but let's not. So what I set out to do today, and spend probably half of my time giving an introduction, is that having seen that, and having seen that it kind of arises a little bit out of the blue. I mean, there was some motivation, but there was no derivation of these equations. You postulate them and they work. I wanted, first of all, to understand the origin of that dual formulation and simplify its derivation. I would like to extend it to a larger class of Calogero type models that in principle might involve non-identical particles, so the interactions are not permutation invariant, and also generalized external one-body potentials, and also give an intuitive and simple derivation of the hydrodynamic limit of these systems with the new potentials. So the nutshell of what I'm going to do is basically this page. We start by considering a set of first-order equations where we have some particle coordinates capital X A, capital X to distinguish it from what I had before. Eventually we will get there. We have little n that many capital coordinates. Each one of them has, in quotation marks, a mass ma, and satisfies a first-order equation like that. So mx dot, something like the momentum, equal the derivative of a function. So at face value, these are not of Hamiltonian form because these are first-order equations. They are more like a friction type of gradient flow. However, if you take another time derivative there, use the fact that this is true within one line, basically, you find out that the mass times acceleration of these particles is given by the derivative with respect to each particle of that total quantity. So that means that this has exactly the form of Newtonian motion in a potential which is given by this term, actually minus that term. And therefore, if you know what you want, if you know that you want to find some interesting system, you can ask what kind of generating function phi you can put there so that this potential be of the type that you want, and move on from there. Usually we don't like, or we don't think it's interesting to look at problems that have more than two-body interactions. Three-body interactions are not very physical, so we would like to have only two-body terms appearing. So we have to take this function, this potential phi there, not potential, the generating function to contain only one-body and two-body terms. We would also like the two-body interactions to only depend on the distance of the particles, not in their individual components, so that we have some kind of translation invariance of that interaction. And therefore, we choose that form. By symmetrizing this in the f's, you can always have these functions fab that in principle depend on the particles, satisfy this relation. That's not a constraint. And for later convenience, we give a name to the derivative of these functions for each particle. Only we give a name to the derivative of these functions to be equal to a new little f times ma and b. That means little f is defined 1 over ma and b times that. Something like that I do also for the derivative of the one-body functions w. They are little m times little w. And then I express the potentials in terms of these functions, and they take the potential, and the potential takes this form. Even though f has only two-body terms, you see that because of the appearance of these two f's here, this in principle could contain three-body terms. And the purpose of redefining these like that is that this product now is symmetric with respect to three particles. So now I will impose the condition that I don't like to have any three-body terms. These three-body terms should reduce to two or one-body terms. That gives me some functional equations here, very similar to those of you who are familiar with the Calogero model, to the functional equations that derive from the quantum mechanical solution of the Calogero model when you solve it in terms of the exponent of the wave function. But these functional equations are in principle particle dependent. All these functions could be different for each pair of particles. All I demand is that such combinations reduce to sums of two-body terms. And similarly, that particular combination that involves the one-body term reduces again to two-body and one-body terms that depends only on the distance of the particles. So these are functional equations that can be solved using standard techniques. If I choose the right-hand side here, if I choose the emergent two-body interactions to be constant, and that's just an assumption, that means these sums of these three terms is just a constant that depends on A, B, C, I can prove that this equation has essentially a unique solution where that thing is a constant independent of the particles. This FAB is again independent of the particles and has these three forms that remind you that will lead eventually to the Calogero, to the periodic Sutherland, and to the hyperbolic generalization of that problem. And the potentials that I get here, you see that they are of this form. They are of the Calogero, Sutherland, or hyperbolic Sutherland model, but the strengths of these interactions are particle dependent because they depend on the masses, because these F's, remember, were defined in terms of masses, and these masses reappear in these strengths. Why did I consider the more general case where this is not constant? Well, you can consider it, and you know already, you don't even need to derive it, that there is a solution of that equation where the form of that prepotential is the Weierstrass function, or the sigma function whose square is the Weierstrass, but something like that. And but because this was a more general form of that equation, where in principle the particles, the terms could be particle dependent, I have no proof, at least none to me, that this is the only solution. So for the time being, I will not consider this because of I want to focus on things that are simpler, but this is actually an interesting situation. For the second constraint involving the one-body terms, a similar analysis shows that these one-body prepotentials, let's call them, parts of the generating function, have these three forms in the rational, trigonometric, or hyperbolic case, and they lead to extra one-body external potentials of this form. You see that it contains strange types of two-body interactions that are of the 1 over x type and particle dependent, and it can have other, oops, there is a square missing here, actually. And they can have one-body interactions of that type. I kind of mumble about it because pretty soon I will move on to something more restricted. It seems that we have obtained a generalized Calogero with sextic 6-order interaction. That's because I had screwed up something when I wrote here. And corresponding trigonometric and hyperbolic potentials and particle dependent, etc. This seems like we have an embarrassment of riches. This seems like quite a dramatic generalization, but it's not quite true. The thing is that the potential energy, as I showed to you before, was negative definite. The potential was the sum of squares of terms multiplied by masses, and that in principle is something positive definite, but the potential was minus that. So the potential energy is negative definite. It has maxima only where the potential becomes 0. So this corresponds to essentially unstable motion, and the first order equations that describe this motion were the motions were describing the motion of particles where they crawl asymptotically and they climb to the top of those unstable equilibrium points. So not a very interesting situation, and of course no sign of those dual variables. The resolution to that is that if you want the potential to become positive definite and therefore stable, you need to reverse its sign, and that can only be done by taking this prepotential to contain I explicitly, to become imaginary. So the potential, being the square of derivatives of that, becomes now positive. The second order equations become stable. This is the second order equation of motion of the particle with positive repulsive interaction, so and corresponding one-body terms. But the problem is that if you do that, the first order equations from which everything arose now become complex. If the x's are real, then all these functions are real. The right-hand side of this first-order equation is purely imaginary. If the left-hand side is to be real, that means everything has to be 0. So this describes a situation where the particles do not move and also satisfy this set of initial conditions, which is a possibility, but it's not very interesting. There is no motion. So how can we get away from it? How can we have real particles with real motion? Of course, you cannot have all of the particles to be real. You would be back into this situation. So what we end up doing is that we say it's enough for us to have a subset of these particles being real. Not everything can be real. So let's choose some of our particles and assume that their coordinates are real, and the rest can go to the complex plane. So we break these capital X's into two sets, the sets of xj and the sets of the remaining ones that I call z alpha. So n, big N plus big M all together are the initial set of particles. This is an artificial separation. And I demand that the xj's are real, while these za's can remain complex. Of course, for this to be an interesting situation, it has to be that the xj's are real and remain real. Because the equations of motion, the first order equations of motion of x, couple them to the z's, that's not guaranteed. So we need to impose some additional condition. The condition is that the second order equations that these x's satisfy, which are of the Calogero type, should decouple between the x's and the z's. If that's true, if you start with initial conditions where all the x's are real, their subsequent evolution will be determined by the second order equation, and therefore they will remain real for all times. And the z's will do their own thing. If you see what that means, and if you demand that all couplings between particles j and particles z, particles x and particles z vanish, you get this equation, which restricts the masses of these particles. That tells you that all the masses of particles have to be equal to each other, and the masses of the remaining variables, the z's that I will call in anticipation solitons, also have to be equal to each other and equal to minus the mass of the particles. The equations of motion now, the first order equations of motion are still coupled. However, the second order equations decouple. And you see that this is a generalization of the dual equations of Abanov, Gromov, and Wigman, but for general, more general functions f here, two-body functions. And I guess the lesson that we get from here is that some of these coordinates z have to remain complex, and that if we interpret them as solitons, the solitons are basically Calogero particles with negative mass that, as a consequence, have to escape to the complex plane. These are some simulations of this system, solutions, but because these are complicated equations, numerical solutions. And this is the one soliton solution. This is the initial condition here, where all these particles sit here. There are n particles here. I don't know, it's about 20 or so, and a single z, a single soliton, and that implies that one of the particles, because there is this soliton, one of the particles will do something special, and that's what happens. The particles start like that. One of them starts moving to the left. It's not really going through, and I wish that the scale of this picture were a little bit different. It simply bumps onto the other particles, and each time that it bumps, it assumes the position and velocity of that other particle, and that other particle moves like a Newton's cradle situation. And eventually the last particle shoots out and goes up to a distance where it exhausts its kinetic energy. It comes back and starts doing the same trick with the remaining particles. Because now the external potential is quartic, the motion is not periodic. Even a single particle in a quartic potential, the motion does not have a fixed period. A single particle in a quartic potential has a period that depends on its energy. And if you have many particles, even in this integrable motion, the overall motion is not necessarily periodic. So you see what these particles do. They start sloshing around, but they also get further away. But this soliton keeps doing this back and forth. It returns, it bumps to the other particles. If you look closely, you see that there are all these turning arounds, but the soliton persists in its motion all these are real particles. I will show you this in a moment. Because there is a single soliton, it drives one of the real particles to behave like that. What happens is that when this soliton's real part is far away from the position where the other particles are, it attracts a single particle. So a single particle has to follow and be close to where the soliton is. So as the soliton moves on the complex plane, a particle follows. When it mixes with the other particles, this picture is not very good. It just creates a deformation of the other particles, but the scales here are not good to show it. So these are all X's. These are all real particles.
Each time you have a crossing, do you have an exchange of particles following the soliton?
No. The soliton is invisible here. The soliton is doing its trick.
But the one which makes the sinusoid, this one,
that
is that an exchange of particles each time, or still the same?
There is an exchange because the particles cannot go over each other. So it's exactly like in Newton's cradle, this thing that things bump to each other. This is the two-soliton solution, about the same picture. There are now two different solitons, and you see again that they slosh around, and as the particles get away from each other, when they go closer, because they have a high velocity, they come closer to the particles, but still, again, that's not the best picture. And here is the answer to what happens to the z's. The z's are happily moving on the complex plane. If you have a single z, this single z moves like a single particle, nothing else to interact, because its second-order equation of motion is a Calogero system in an external quartic potential, but there is a single z. So it's a particle in external quartic potential, only allowed to move on the complex plane. And see what it does. It starts here and does this. A motion of a particle on the complex plane under cubic forces or quartic potentials, everything complex, as far as I know, does not have to be periodic. So it's kind of surprising that it goes through the same point on the x-axis each time that it goes around, and it has this kind of regular pattern. I don't know yet why this is true. There are mathematical properties of that motion on the complex plane that I'm unaware of. And it's even more surprising when you have two of them. One starts here, the other starts there, the blue and the red one. And you see that, not the blue, not the red, the black and the blue, I guess. You see that the black one does exactly the same motion as before and comes closer and closer to the real axis, while the other one does the same motion and comes further and further apart. And again, they go through the same point. I don't understand why. Perhaps that was an artifact of the initial solutions chosen in these numerical simulations. But that's what the solitons do. Yes?
Does it happen something special on the real part, or on the other part? Because when at the time when this soliton passes through the special point?
Yes. When this soliton passes through the special point, it's exactly the time that this particle that follows the soliton when it goes away reaches its inflection point, reaches the maximum. And then goes back. So that's what this represents. But why the motion of the complex variables has to go through the same point in the real axis, I admit that I have no proof or understanding. Okay, let's move to the, so that was basically what I had to tell you about the n-body problem. Let's move to the hydrodynamic limit, to the limit where you take a continuous distribution of such particles. We will have particles with real coordinates and what I call solitons with complex coordinates, and I will let the number of particles go to infinity so that they form a dense fluid, essentially. The number of solitons can remain finite. That I will not take to be anything special or to go to infinity. What I'm interested in is that the real system becomes like a fluid. To do that, we need a way to monitor the position and velocities of particles in a way that is convenient to take the limit of dense particles. And you may say, well, why don't you start with the equations of motion of the x and take the limit that there are many of them? You could do that. But that's more complicated, and that doesn't lead to a form of these fluid equations that I call the chiral Benjamin-Ono form. So again, I will use a little trick here. The basic device is that I will introduce one more particle to the system, fictitious mathematical device if you wish, that I call the spectator particle. I will call it the A equals 0 particle to distinguish it. It will have some coordinate x0 that I will simply call x, and some mass m0. So now I have n particles plus n z variables plus 1 over altogether variables. The total system remains Calogero-like. The same equations of motion are satisfied as before. But the spectator particle should really be a spectator. That means it should watch what is happening without interfering with the remaining particles. And that means that any interaction that it creates to the other particles, which has this term and the corresponding second order terms, should go to 0. That means that you must take the mass of this particle go to 0, so that these terms be driven to 0. You may think that if you do that, everything becomes trivial, but it's not true. The equations of motion of the particles and solitons remain now the same as before. Every remnant of that spectator particle has disappeared, but the equations of motion of the spectator particle itself have a well-defined limit. And that limit contains that motion contains information about the remaining particles. So I like to call it a pilot fish, which is like this small fish that swims close to a shark, that it follows the motion without disturbing the motion of the bigger system. So this is what these equations for the velocity and acceleration of that pilot fish particle is, the spectator particle. The velocity of that particle I will simply call u, and it will be my main variable. And you see that it depends on the position of that particle, but also on the positions of all the other particles and the solitons, and satisfies this equation of motion. The final twist is that if you have one particle, you can only observe this combination of variables, but if you sprinkle the system with lots of such particles, if you consider that you have a distribution of such spectator particles almost at every position in x, then these particles, these monitored particles, eventually follow the motion of the remaining particles, and they are a mathematical device so that you'll be able to see what the other particles do. It's a little bit like throwing sawdust on a river that you cannot see exactly where the water is going. If you throw sawdust, you see exactly where this dust is going, and you can see the motion of the fluid. So that means that I promote the velocity of this spectator particle u of x to a field u of t, to a field, the field u that depends on x and t. That means for all different particles that start at position x, this is their velocity, so it's a function of that x and of time. When I do that, and I promote this to a field, I have to be careful when I define the time derivative of that field. Du over dt is, by definition, the derivative of this field when I vary t keeping x constant, but x is the position of the particle, of the spectator particle, which evolves itself in time. So I have to be careful to note that this is not the derivative of u with respect to t. This is the total derivative. This simply means that the partial derivative of u with respect to t is only the part of the derivative which is due to the dependence of that u on the remaining particles, not on the position x of the spectator particle itself, which is the total derivative minus the part that depends on the particle x itself, which is du dx times x dot, and x dot was u itself. So you get this, and people who have done or dealt with fluid mechanics will recognize that. That's basically the particle fixed velocity, and that's the convection term that will give you the time derivative, or transport term, I guess. So that's good, because now we can use the equation of motion for du dt, and that plug it in this equation. That will give us the equation of motion partial u partial t of that field. In doing that, there are some technical issues that I don't want to go into here because they are not very interesting. When you do that, you would like to express all the terms that appear in these equations involving the other particles xj and the soliton za back into the field u itself, u of x. You see that this is only possible when you split u into two parts, kind of one depending on z and 1 depending on x. And in terms of these two fields, you obtain this equation. It involves u, but it also involves separately the two parts. U plus plus u minus are u, but here is the difference of those two that appears rather than the sum. And this is a bichiral version of the Benjamin-Ono equation. This is a generalization of the equation of Abanov, Gromov, and Wigman that they had derived for more general external potentials. This equation, as I stated it, although it involves a continuous field u of x, is actually true for finite n and finite m. I haven't yet taken the limit n going to infinity. I didn't have to. And of course, the concern that you may have is that I started with the field u, but now I introduced two fields, u plus and u minus. So I have one equation for two fields. How does this work out? Actually, because of the analyticity properties of these fields, everything is fixed. If you look at the equation for u plus, you see that u plus has poles. Maybe I can show you. Where was it? Here. U plus has poles because this function here has singularities whenever each x goes to z. So this function, where am I? Here. This function u has poles in the real plane. Oh, it was here too. I didn't need to go back. And therefore, if you identify these poles, no, that's another relation. Okay, that's the question of motion. The definition of u has poles. The poles in the complex plane tell you where all the particles z's are, so that fixes the z's. The equations for z's then fix the particles x, and that fixes the form of u minus. For that, you need to know how many other particles there exist. I fumbled that a little bit when I said it, but what I want to stress is that if you start with one of those fields, using the analyticity properties of these fields and the knowledge that there are n other particles, you can recover everything. You can recover u minus and put into your equation. So this is a good start of something that is kind of independent of exactly how many particles n have, and therefore you can take the large n limit. Again, I don't want to go through the details here. You end up having to calculate sums like that when the number of particles becomes large and the particles come close to each other. A naive continuum version of this does not work because this has singularities, and these singularities have to be treated carefully. In this well-known relation that the sum of a function over integer is the sum of the Fourier transform of the function of the corresponding dual integers is useful because it gives us both the perturbative and the non-perturbative corrections to these continuum expressions. So I will just state the final result. In the continuum limit, u plus becomes this particular function of the particle's velocity and density field. So that's the fluid now. And you see that it involves this Hilbert transfer or generalized Hilbert transfer, where the kernel is this f that defines what kind of Calogero system you have, and this extra term here. And u minus, you see that it has a discontinuity on the real axis, which is proportional to the density of particles. U minus had poles at the position of each particles. These poles condense to a full line when you have a continuum, so it leads to that discontinuity. Still, they satisfy the same equation as before. I flash here by saying that the above results are perturbatively exact to all orders in 1 over n. You may say that if n is not infinite, but it's finite, are these results exact? Well, they are almost exact. They contain all 1 over n corrections. The only corrections that they do not contain are of order e to the minus n, completely non-perturbative. They correspond to adding to having neglected or omitted instanton contributions there. They become important when you have non-perturbative situations where the fluid breaks into two components, but in every other, that you can deal with separately.
You can control these.
I'm sorry?
Can you control these errors that you're making?
For any finite n, all I know is that they are of this order. Of course, when you take the large n limit, then this becomes completely insignificant. The reason why even in the large n limit you have to keep these non-perturbative corrections is that the soliton is quite sharp, so it contains terms that if you thought that they are subleading in 1/n and throw away, the soliton will start diffusing. You have to keep higher order terms in 1/n to make the soliton stable. Only the non-perturbative terms you can really throw away. Okay, let's see what. So, finally, we can derive the equation of motion for the fluid. That means we take these expressions for u plus, u minus. You put in this bidirectional Benjamin-Ono equation that I showed you. You decompose into real and imaginary parts, and you end up with these two equations. This one you recognize as the continuity equation, conservation of the number of particles. This is the particle current. And the second one is the Euler equation. It gives you the, well, you can compose this and that term as the acceleration term of particles, and everything else here is an external force. That part is the external potential, is due to the external potential, but everything else has to do with the interaction between particles. And they do arise from this Hamiltonian, which is actually the same or related to the Hamiltonian that I showed you several transparencies ago when I talked about the collective field formulation. It's just that we have expanded a square and used some identities. And if you use these Poisson brackets, it gives rise to these equations. And the thing that we gained, other than having this equation, is that by using u plus and u minus, which have a relatively simple form if there are few variables za, if you assume that u plus has, say, a single pole in the complex plane, you can solve these equations almost explicitly, and you can find soliton and nonlinear wave solutions. Soliton means that you have a finite number of z's that move on the complex plane, that induces a particular form for u, and that induces a particular form of density and velocity. Nonlinear waves actually means having a periodic collection of solitons. You have solitons that periodically repeat themselves and they move in tandem. So it's like having a set of solitons in fixed distances, and when you sum them, they give rise to a wave of this particular periodicity, this particular wavelength, but it's a nonlinear wave. It would become disjoint solitons if the distance is big, but as the solitons come close to each other, it really looks like a wave. And if the solitons become dense, this becomes a sound wave. Well, that was basically the full story. This is the generalization of the corresponding results of Abanov et al. That I wanted to obtain. We also have solutions for the fluid, but I didn't reproduce here. So I'm just out of time, so I will conclude with some open questions and outlook. Clearly, there are lots of open ends here and things that have not been addressed. One is that all these external potentials that I got were of the restricted Bogomolny type. That means they were of the type where they are a perfect square. Yet I know that the system remains integrable even when the potentials are not of that perfect square type. Here I only obtain those. Why? Is there a natural way to obtain these other ones? This slightly more general by one parameter set of potentials. Also, I talked to you about integrability here, but all I showed you was a way to reduce a set of first-order equations to a set of second-order equations without having unwanted three-body and other terms. I never actually addressed the issue of integrability. And yet, the potentials that I get imposing these requirements are exactly the ones, even a subset of those that are integrable. So is there a proof of integrability within this framework? This is work in progress. There are some intriguing indications of integrability. It turns out that if you take at face value the systems that I showed you and calculate the integrals of motion of the Calogero system that you know they exist, they all vanish. I say, that's crazy. Well, it's not crazy, because remember that the system consists of particles and solitons, and the solitons come with a negative mass, and all their contributions to the integrals of motion are negative. So what happens is that you have quantities cancelling each other. Of course, if the sum of a positive and a negative term is 0, that doesn't mean that each one is separately conserved, so that's why this is still work in progress. All this was entirely classical, because in principle it didn't even have a canonical formulation, although you can eventually define, I didn't show you, you can define a canonical structure. So the question is, how would you do that in the quantum mechanical domain? This has to do with the fact that when you have a finite number of solitons, this imposes restrictions to the initial value data of the particles, and some of these initial value data lead to a kind of metastability that requires soliton condensation, but let's not elaborate on that. There are many allusions to other things here. There are allusions to quantum mechanics on the grounds that this generating function phi that I showed you behaves a lot like the exponent of the quantum mechanical wave function of a many-body system. Now, there is no reason why that exponent would correspond to a motion of particles in the way that I showed you, but yet the similarities are uncanny. The kind of potentials that I get are reminiscent of supersymmetric quantum mechanics and supersymmetry breaking when you have the potential becoming of the type that goes away from this Bogomolny type, and so on and so forth. Vincent also pointed out that what I did seems quite similar or reminiscent of Backlund transformations. So all these are connections that have to be worked out. I would very much like to generalize this to spin Calogero models where the particles carry, each particle carries some kind of internal degrees of freedom. Classically, they can be some compact degrees of freedom. Quantum mechanically, they become spin. But that's still an open problem. It would look that this should be easy, but it's not, because the degrees of freedom that have second order equations of motion, like the coordinates, have now been made first order. The spins have already a first order equation of motion. They are their own phase space. So it's not clear how to incorporate them in this formalism. And finally, I explicitly omitted or chose not to look at the elliptic case, the case that the solution to these functional equations was the most general, most complicated one. That's, from a certain point of view, the most interesting situation, because there are no known integrable one-body potential. That means the Calogero model with elliptic potentials is integrable, but there are no generalizations where the particles also feel external one-body potentials. Yet, the outcome of this is that such potentials must exist, and that's also work in progress. And that's all I had. Thank you. Minus 1 over m.
Yeah.
That's like a dual one.
It's a different type of duality.
It's a different type of duality, you're right. So it's not quite like this. If you take the classical equation of motion of the fluid, okay? And there, instead of working with the classical coupling, whenever you see g squared, you put it g times g minus 1 and so on. If you take the full equation that you get by reducing the many-body quantum mechanical system into this second-order Benjamin, or this Andrich, Yevitsky, and Levine equation, and you look for solitons, first of all, there is a priori no reason why you should keep h-bar corrections there, because this is a classical system. So what's the point of keeping h-bar corrections there without quantizing the excitations themselves? However, if you do it blindly, you end up with a situation that the solitons are like a composite of a particle of mass, of a particle number 1 and of a particle of 1 over g, of minus 1 over g. So that's again reminiscent of another type of duality. The g goes to 1 over g duality. Now you have the Veselov system where you have m and minus 1 over m. There must be some unifying picture there, and I would like to know a little bit more about it if you have any ideas, because I don't know what that picture is.
Do you take only n to infinity?
Can
Do you take
then you end up with a condensation of solitons. You must talk about a density of solitons on a complex plane. And that's actually a very interesting situation. I have commented it not here but before. In some situations, to even have a solution for the particle system, even in the finite n case, you need such condensation of solitons, because otherwise the particles become unstable. So I think there is a lot of structure there. I don't know a priori what is the answer, but in principle you can describe the solitons in terms of their own complex plane density and see what happens. If m is greater than m, then the roles are reversed. You only need solitons, as many solitons as particles, to describe the most general motion of the particles. If you have more solitons than particles, you have a redundancy. The same particle motion corresponds to more than one different type of soliton. So now the soliton system has become richer, and the particles are driving the solitons, if you wish. Okay, thank you.
So your Alexios is